Hello and welcome to Scholar Fedu. This is our UTME prep series where we provide relatively detailed solutions and explanations to the UTME questions. And in this recording, we're looking at the UTME questions for physics for the year 2014. This is the second part of the recording. We are going to look at the next 25 questions. Before we continue, please don't forget to subscribe to our YouTube channel, like and share content. You can also visit our website at scholar.com to practice the UTME exam for free. Alright, first question here on wave. The distance between two successive crests of a wave is 15 centimeter, and the velocity we are given as 300 meters per second. We have to calculate the frequency of the wave. Alright, the wavelength is given as 15 centimeter. Now, we do not have wavelength directly. You can say the word wavelength does not even appear in the question. So how come we are taking this to be the wavelength? That is because we've been given the wavelength here by definition. The distance between two successive crests in a transverse wave, okay, is what we call wavelength. The distance between two successive crests or trough in a transverse wave is its wavelength. Okay, so we already have wavelength from here as 15 centimeter. Okay, and the velocity we are given here as 300 meters per second. Now, in order for these units to be balanced, here is centimeter and here is meter, we need to convert this to meter. Okay, we cannot use centimeter directly with meter. So to convert from centimeter to meter, we divide by 100. Okay, so we have 15 divided by 100, that is 0.15 meter. Then we recall this formula here, that the velocity of a wave is equal to frequency times the wavelength. Then in this question we're looking for the frequency, so we are going to make the frequency the subject of the formula by dividing both sides by this wavelength here, the lambda here. Okay, so we're going to have v over lambda is equal to f, the frequency. The velocity is 300 divided by the wavelength, which is 0.15. okay, 300 divided by this will give us 2000. You can write 2000 as 2.0 times 1000, and 1000 is the same as 10 raised to power 3. So we're going to have this as 2.0 times 10 raised to power 3. Now this should be a superscript. Okay, this is not 103, it should be 10 raised to power 3. Alright, next question on wave. A boy receives the echo of his clap reflected by a nearby hill 0.8 seconds later. How far is he from the hill? Alright, so the velocity or speed, okay, of the sound that the boy produced is going to be equal to 2 times the distance over t. Now normally speed is just distance over time, but here we are using 2d, like 2 times the distance. Why? Because an echoed sound travels through distance. It travels through distance, the distance to the reflecting surface, okay, and the distance from the reflecting surface. Okay, it travels through distance, one distance to the reflecting surface and that distance back to the listener. Okay, so that's why I'm using 2d here. And in this question we want to calculate the distance. So what do we do? That is the how far the boy is from the hill, that is his distance from the hill. So to do that, here we will make the distance the subject of the formula. We will cross multiply this t here, so we are going to have vt is equal to 2d. Then we are going to divide both sides by 2, so we are going to have d is equal to vt divided by 2. Now from the question they've given us the time already as 0.8. The speed of sound in air, we know that already to be 340 meters per second. So we say the distance is equal to the speed 340 times the time is 0.8 divided by 2. So by the time we do this, multiply this and divide it by 2, we'll be getting 136 meters. That is the distance of the boy from the hill, 136 meters. Next question. The diagram above shows a stationary wave of wavelength 40 centimeter in a closed tube. The length L is of the resonating air column S. Now this thing that I have here, just this here, the length of this column here is 1 over 4 lambda. The length of this column here, this one here, is 1 over 4 lambda. If you now look from here to here, how many of these things we can find? We have 1, this is 1, this is another one, this one that is inverted here is another one, that makes 2, and this is another one. So that means that the length here is now going to be 3. Since we have 3 of this thing here, 3 times the length of each of them, which is 1 over 4 lambda. I hope this is understood. The length of this, like this alone, is 1 over 4, and we have 3 of it here. This is 1, 2, 3. So the length of the 3 is going to be 3 times 1 over 4. So you're going to have L to be equal to 3 lambda over 4. This lambda here means the wavelength, and the wavelength in the question they gave us to be 40 centimeter. So this will just be 3 times 40, that's 120, divided by 4, and that will be 30 centimeter. Next, on optics, an object is placed 10 meter from a pinhole camera of length 25 centimeter. Calculate the linear magnification. Alright, the magnification is equal to the image distance over the object distance. Okay, now the object distance there is 10 meter. Okay, an object is placed 10 meter from a pinhole camera, so the distance between that object and the camera is 10 meter. Now they said the pinhole camera is of length what? 25 centimeter. The image is formed inside the pinhole camera at the back. Okay, now the distance that is going to be between the pinhole of that camera and the back of the pinhole camera is going to be approximately equal to the length of the pinhole camera, of that camera, that device itself. So the image distance there is going to be 25 centimeter. Now if you look at this, the object distance is in meter and we are given this in centimeter. So what do? We need to balance our units here. The unit needs to be balanced. So to do that, we will convert this to centimeter, or we convert this to meter rather, so that both of them can be in meter, or you may choose to convert this to centimeter so that they can both be in centimeter. But your best bet is to convert to meter. Okay, so we are going to convert this to meter. So convert from centimeter to meter, we divide by 100. So this is going to be 25 divided by 100, and so we have 0.25 meter. Now we can now use this formula for magnification there. That magnification is equal to image distance over object distance. The image distance is 0.25, so we divide that by the object distance, which is 10. 0.25 divided by 10 will be 0.025. If you write this in standard form, this is going to be 2.5 times 10 raised to power. If you look at this, we have shifted this this decimal point here to here, so we need to count from here. How many jumps do we have here? Like 1, 2 to this point. So this will be 10 raised to power minus 2. Okay, and we are using negative power here because this number is even a number that is less than 1. It's a number less than 1. It's not even up to 1. Okay, this is a number less. Anything in 0 point is less than 1. And if you write it in standard form, you are going to have 10 raised to power minus something. Okay. Next, also on optics, the focal length of a concave mirror is 2.0 centimeter. If an object is placed 8 centimeter from it, the image is at. Alright, so here we have the focal length as 2.0 centimeter. The object distance, the distance of the object from that concave mirror is 8.0 centimeter. So we want to calculate the image distance. To do that, we are going to use what we call the length or mirror formula. That is 1 over f, the focal length, is equal to 1 over u plus 1 over v. Then since we are looking for v, we are going to make it the subject of the formula. How do we do that? We will bring this 1 over 4 to the other side, so that this is going to become 1 over f minus 1 over 4 is equal to 1 over v, or we can write it like this. This will then be 1 over f, the focal length, which here is 2, minus 1 over u, which is 8 here. Next, we then take the LCM of 2 and 8, that is 8. Then we say 2 in 8 is 4. 4 times 1 here is 4. Minus 8 in 8 is 1. 1 times 1 is 1. So you have 4 minus 1 over 8. 4 minus 1 is equal to 3 over the 8 that we have here. So you have 1 over v is equal to 3 over 8. To get the value of our v here, what do? We are going to invert, okay, both sides of the equation. That is, we will turn it down. So this 1 over v, we are going to turn it upside down. It will become v over 1, and that is v. And this 3 over 8, we also turn it upside down. Whatever you do to the left side, you do to the right side. So we will turn this 2 upside down, and this will become 8 over 3. 8 over 3 is approximately 2.7 meter. Now this is not very consistent, because if you look at the units from the question, they are in centimeter. Okay, just assume that it is meter. Okay, that is supposed to be meter. All right, just assume that this should be in a compound microscope. The objective and the eyepiece focal lengths are, both lenses are of short focal length. Okay, the focal length of the eyepiece lens and objective lens, both of them are short, but that of the objective lens is even shorter. Okay, is even shorter than that of the eyepiece. Next, when a telescope is in normal use, the final image is at. So this is a ray diagram of a telescope, okay, in normal use. When you have a telescope in normal use, the final image formed is going to be at infinity. Okay, the final image will be formed at infinity. But if it is in abnormal use, the final image is going to be formed at the near point. But for this, it is about normal use. Okay, so it will be formed at infinity. Next, on current, when a negatively charged rod is brought near the cap of a charged gold leaf electroscope which has positive charge, the leaf. So when you are using the gold leaf electroscope to test for the charge on an object, and you bring that object close to the leaf of that gold leaf, divergence, okay, is going to, the leaf is going to diverge if those objects, if it is opposite, like if the charge on the leaf and the charge on the object they are bringing close to it, if it is opposite, there's going to be divergence. Okay, but if it is of the same, there's going to be closing up of the leaf. All right, so in this case, we are bringing the negatively charged rod to the cap of a good leaf that has positive charge. So what we are going to have here is divergence. Okay, divergence is going to happen. Okay, the divergence of the cap is going to occur because the rod they are bringing, or the body they are bringing close to the cap, is of an opposite charge to the charge on the cap. Next, also on electricity, what charge is stored in a 0.1 farad capacitor when a 10 volt supply is connected across it? The charge Q stored in a capacitor is equal to the capacitance times the potential difference, and here we are given the capacitance as 0.1 times the potential difference here is the voltage supply, that's 10 volts. 0.1 times 10 is 1, so you have 1 coulombs as the charge here. Next question, we have to calculate the effective capacitance of the circuits above. Now in this circuit we have some capacitors connected in parallel, and then we have these other ones here. Okay, so what do we do? How do we find the effective capacitance here? We are going to first find the effective capacitance for these ones that are in parallel. Okay, for these ones that are in parallel, we find the effective capacitance. Whatever we get for the effective capacitance is now going to be in series with these other ones here. Whatever we get for the effective capacitance of these three here is going to be in series with these other ones. Now, how do we get the effective capacitance when you have capacitors in parallel like this? We simply add up the capacitances. So the effective capacitance of these three here, let's represent that as CP, is going to be equal to the sum of each of these capacitances here, 2 plus 2 plus 2, and that is 6 microfarad. Now that means that 6 microfarad, that's the effective of this, is now going to be in series with what? 3 microfarad and 2 microfarad. Then we find the effective capacitance. So for that, we are going to be using this formula here. When we have 3 capacitors connected in series, let's say capacitor 1, C1, C2, C3, okay, the effective capacitance is going to be given as 1 over CT equals 1 over C1 plus 1 over C2 plus 1 over C3. Now I want us to take this as C1, take this as C2, and take the effective of this ones here as C3. So this is now going to be 1 over CT is equal to 1 over 2, that's C1, plus 1 over C2, that's 3, plus 1 over C3, the effective of what you have here, and that is 6. So what do we now do here is we have 1 over 2 plus 1 over 3 plus 1 over 6. We will take the LCM of the denominators, that is the LCM of 2, 3 and 6, and that is 6 here. Then we say 2 in 6, 3, 3 times 1 is 3, plus 3 in 3 is 2, times 1 we have 2, plus 6 in 6, that's 1, times 1 we have 1. So then we have 3 plus 2 plus 1, and that is equal to 6 over 6. So you have 1 over CT is equal to 6 over 6. If we reduce this to lowest term, we can divide the numerator and denominator by 6. So 6 here 1, 6 here 1. So you have 1 over CT is equal to 1 over 1. Comparing both sides of the equation, 1 will match to 1 and CT to 1. So 1 to 1, CT to 1. So the total or the effective capacitance of this circuit here is going to be 1 micro. Alright, next on electricity. The maximum power transfer occurs in a cell when the external resistance is, for maximum power transfer in a cell, the external resistance must be equal to the internal resistance, must be the same as the internal resistance of the cell. Next on electricity, if a wire 4 meter long and cross-sectional area 0.8 millimeter square has a resistance of 6 ohm, find the resistivity of the wire. Okay, so the length here is given as 4 meter, the length of the wire. The cross-sectional area of the wire is 0.8 millimeter square. We need to convert this to meter square. Okay, we need to convert it to meter square. To convert to meter square, we will divide this. Now, if you want to convert from just millimeter to meter, you divide by 1000. Okay, you divide by 1000. But if we are converting from millimeter square to meter square, we are going to divide by 1000 twice. Okay, you divide by 1000 two times. That means you are dividing by 1000 times 1000. So you are dividing by 1 million. Okay, you are dividing by 1 million. So you are dividing this by 1 million. Now 1 million is 10 raised to power 6. That is 10 multiplied by itself 6 times. Okay, dividing by 10 raised to power 6 is the same thing as multiplying by 10 raised to power minus 6. Okay, dividing by 10 raised to power 6 is the same thing as multiplying by 10 raised to power minus 6. So what I'm doing here is dividing this by 1 million. And how am I dividing by 1 million? By multiplying it with what? 10 raised to power minus 6. Now from here, this is 0.8. We can write it in standard form as 8.0 times 10 raised to power minus 1. Okay, 8.0 times 10 raised to power minus 1, then times this 10 raised to power minus 6 from here. Now we are going to have 8.0 times, we use our law of indices on these two here. Okay, that's what we are going to say. This will be 10 raised to power minus 1 plus minus 6. 10 raised to power minus 1 plus minus 6. Minus 1 plus minus, that is plus times minus, that will become minus. So we are going to have minus 1 minus 6, and that is minus 7. So we have this as 8.0 times 10 raised to power minus 7 meter square. Okay, then our resistance from the question is 6 ohm. So we are now looking for the resistivity, denoted by this symbol here, rho. The resistivity is going to be equal to the resistance times the cross-sectional area divided by the length. Okay, so we have resistance 6 times area 8.0 times 10 raised to power minus 7 divided by 4. So we are simply going to do here, what I've done here is divide this 6 here by 4. Just divide only this 6 by 4. So you just say 6 divided by 4, that is 1.5. So you now have 1.5 times 8.0 times 10 raised to power minus 7. 1.5 times 8 will give us 12. Okay, so it's 12 times 10 raised to power minus 7. Now this 12, I can write it as 1.2 times 10. Okay, if you do 1.2 times 10, that is 12. So and that 10, you can write it as 10 raised to power 1. Since anything raised to power 1 is that same thing, that is 10 raised to power 1 is the same thing as 10. Okay, and 1.2 times 10 is what? 12. Then I'll use my law of indices here. So this is where I'm going with this. Okay, this is where I'm going with this, because I want my answer to be in this form. Because everything that I have here is something point something, and what I have here is 12. So I have to write it as 1 like something point something, like 1.2. Okay, so that's why I've written this 12 here as 1.2 times 10 raised to power 1. So I'm now using law of indices on this. So this is going to be 10 raised to power 1 plus minus 7. That will become 10 raised to power 1 minus 7. 1 minus 7 is minus 6. So our resistivity here is going to be 1.2 times 10 raised to power minus 6. Next, also on calculation, on electricity, has to do some calculations. A circuit has a resistance of 200 ohm. The resistance of the circuit can be reduced to 120 when. So there's some simple things that I want us to reason out here. Okay, is that when resistors are in series, when you connect resistors in series and you want to find the effective resistance, what do? You are going to add up the resistances, right? Now if you now have a circuit that already has a resistance of 200 ohm, okay, that's already there, and you want to reduce that resistance to 120 ohm, definitely you cannot be adding another resistor to it in series. You cannot, because if you add to it in series, it will even increase, okay, beyond this 200 and beyond this 200. Okay, so these options that have series and series, they are out. So we know that here we need to be adding another resistance to that circuit, another resistor to that circuit in parallel. Okay, in parallel. But the question will be, what is going to be the resistance of that resistor? Okay, because here we have two options that are parallel here. This one is saying 300 in parallel, this is 150 in parallel. So what is going to be resistance? That's what we need to calculate. All right, now what we want to achieve here is that we want the effective resistance, okay, to be 120 ohm. 120 ohm, right? Now if you have two resistors, okay, that are connected in parallel, let's say the resistors are R1 and R2, they are connected in parallel. Let us, if you represent the effective resistance as, let's say, RE, for example, then you are going to have 1 over, you are going to have 1 over RE is equal to, then you have 1 over RE is equal to 1 over R1 plus 1 over R2. But the effective resistance that we already have it here. Okay, this is the effective resistance. This is the desired effective resistance that we want here. So we just say 1 over, instead of RE, that will be 120 ohms, is equal to 1 over R1 means one of the resistance. Okay, and that here is 200, like the one we already have, plus 1 over R. This R is now going to be the resistance of the resistor that we need to connect to that circuit in parallel. So to isolate this here, we are going to bring this one to the other side. We just bring this 1 over 200 to the other side. So that means on this side we are going to have 1 over 120 minus 1 over 200. Then we take the LCM of 120 and 200, that is 600. Then we say, what is 120 in 600? That is 5 times 1 is 5, minus 200 in 600 is 3. 3 times 1 is 3. So here we have 5 minus 3 over 600. 5 minus 3, that is 2 over 600. So if you reduce this to the lowest term, 2 here 1 and 2 here is 300. So you have 1 over R is equal to 1 over 300. So 1 matches on to 1 and R to 300. So to reduce the resistance of this circuit, we have a website at scholar.com where you could practice exams for free, the UTME exam and the post UTME exam. It also features modular quizzes in physics, chemistry and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at scholar.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next, PHCN measures its electrical energy in the Power Holding Company of Nigeria measures its electrical energy in kilowatt hour. Next, on magnetism, what is the best method of demagnetizing a steel bar magnet? The solenoid method is the best method for magnetizing and also for demagnetizing. And what happens is to demagnetize the magnet, the current is simply run through it in the opposite direction. That is, if in magnetizing it was run in the clockwise direction, okay, then in demagnetizing it will be run in the anti-clockwise direction. The solenoid method is basically the best method for making a magnet, for magnetizing, okay, an object, for making it a magnet, and for demagnetizing it. So other methods are hammering is also one, heating is also one, but the best is what we have from the question. The best is what we have to define from the question, and that is the solenoid method. Well, finding it is not an effective way. Next, also magnetism. The magnitude of the angle of dip at the equator is, so the angle of dip, okay, is the inclination, okay, the inclination to the horizontal, okay, and at the equator, at the magnetic equator, there is no dip. So the angle of, because the angle of inclination, you have this thing here directly in the horizontal, so there is no inclination whatsoever, okay, it's just parallel, completely parallel, so there is no dip. So the angle of dip there is 0 degree. But at the poles, okay, at the poles you have maximum dip. That is the angle between this, okay, the north magnetic pole and the equator, or the horizontal of the earth, is going to be 90 degrees, and that is like the highest that you can have. Okay, that's like the highest that you can before you switch into, a different sphere entirely. Next, we have a diagram here. Use the diagram below to answer the question that follows. The diagram above is that of. Alright, how do we identify a step up or a step down transformer? Is look at the windings on the input and the output, or the primary coil and the secondary coil. If the output is greater than the input, then this means this is a step up transformer. If the input is greater than the output, then that's a step down transformer. But apparently from here, the windings on the output is greater than you have on the input, so this is a step up transformer. Alright, using the same diagram, the electromotive force in the secondary winding, that is on this output side, is now the electromotive force, okay, in a transformer, the EMF, it varies directly as the number of turns or windings. And as you can see in this secondary, okay, the turns are increasing, so it's increasing, okay, it is increasing. So the electromotive force in the secondary winding here is increasing. Alright, nuclear physics. What type of reaction is represented by the following scheme? So if you look at this reaction here, we have two light nuclei combining to form an heavier nuclei. If you look at this nucleus, they have an atomic mass of 2. Okay, the X and Y here, this atom X and Y, they have an atomic mass of 2, and they are combined to form an atom that has an atomic mass of 3. Like, this is heavier than either of these two here. So this type of reaction, we have lighter nuclei combining to form an heavy nucleus, okay, with the emission of energy, loss of energy accompanies that process. This is what we term as nuclear fusion. That is nuclear fusion. Okay, the opposite is nuclear fission, where an heavy nucleus is going to split into lighter nuclei. But what we have here is fusion. Two lighter nuclei combining to form an heavier nucleus. You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2, or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram, you could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at scholar.com, or you could also check it out in the video description below. Next, when an atom undergoes a beta decay, the atomic number of the nucleus. Alright, in a beta decay, the atomic number of the atom that is undergoing that decay is going to increase by 1, while its atomic mass will remain unchanged. Okay, that is in a beta decay. Where you have a beta decay, when you have an alpha decay, if it's an alpha decay, the atomic number is going to reduce by 2, while the atomic mass will reduce by 4. Okay, but in a beta decay, the atomic number is going to increase. Okay, there's no reduction, so it will either increase by 1, while the atomic mass will remain unchanged. Next, we have to calculate the mass of the copper deposited during electrolysis when a current of 4 ampere passes through a copper salt for 2 hours. We are given the electrochemical equivalent of the copper Z as 3.3 times 10 raised to the power minus 7 kilogram per Celsius. Sorry, kilogram per coulomb, brother, per coulomb. Alright, from Faraday's first law of electrolysis, we have M to be equal to ZIT. Z, the electrochemical equivalent of the substance, I is the current, and T is the time. And from the question, we already have all of this. Okay, so Z is this 3.3 times 10 raised to minus 7 times the current, which is 4, times the time that they give us here is in hours. We need to convert it to seconds. How do you convert it to seconds? We are going to first convert it to minutes by multiplying it by 60, then we convert it to second by multiplying by 60 again. Okay, so this becomes 2 times 60 times 60. So we have this 3.3 times 10 raised to the power minus 7. This is on this side. Now 4 times 2 times 60 will give us 28,800. Okay, all right, this will give us 28,800. Then we are going to write this as 2.88 times like 10,000, and that is 10 raised to power 4. 10 raised to power 4 is 10 times 10 times 10 times 10, that's 10,000. So just write this 28,000 as, 28,800 as 2.88 times 10 raised to power 4. How did we get raised to power 4? So we are putting the point here, right? We are putting the point here, like 2 points. So we are going to count from where we are putting the point to the end of this number here. So we have 1, 2, 3, 4. So this will be 10 raised to power 4. Okay, then we are going to do this 3.3 times 2.88, that will give 9.504. Then multiply this by, we now use our law of index on this 2 here. 10 raised to power minus 7 times 10 raised to power 4. If I have 10 raised to power x times 10 raised to power y, that is going to be equal to, according to using the law of indices, you are going to have 10 raised to power x plus y. So 10 raised to power minus 7 times 10 raised to power 4 is going to be equal to 10 raised to power minus 7 plus 4. Minus 7 plus 4, that is minus 3. So you have 9.504 times 10 raised to power minus 3. Approximately this is 9.5. So you have 9.5 times 10 raised to power minus 3. Next, which gas produces a pink colored light in a discharge tube? That is air. Okay, air. The water vapor in the air is what is responsible for the pink color. Okay, the pink colored light that it gives in a discharge tube. Okay, nuclear physics. When lead, okay, decays to lead with atomic number 82 and atomic mass 210, decays to another isotope, okay, with an atomic number of 80 and an atomic mass of 206, it emits. Alright, now there can be changes in the atomic number and the atomic mass of an atom that is undergoing a nuclear reaction depending on what it emits. Okay, now if it is alpha particle that it emits, the alpha particle is an helium nucleus. Okay, what will happen is that the atomic number of that element is going to reduce by 2, while the atomic mass will reduce by 4. Okay, the atomic number will reduce by 2, while the atomic mass is going to reduce by 4. And if you look at what we have here, that's exactly what has happened here. The atomic mass of this lead has reduced by 4 and the atomic number has reduced by 2. So that means it emits an alpha particle. It has emitted an alpha particle. If it is a beta particle that it emits, nothing will happen to the atomic mass. It will not change. Okay, while the atomic number is going to increase by 1. So this would have been, if it is a beta particle that it emitted, this will remain 210, while this one is going to become 83. There will be an increase. Okay, but here there is a change in the atomic mass, so that cannot even be beta decay. Sometimes it may be a beta, like an alpha and a beta particle may be emitted. For example, had it been this was, let's say, 81 now, if this was 81, that would mean that, okay, the atomic mass has reduced by 4, while the atomic number reduced by 2, then increased by 1. Do you understand? If this reduced by 2, that means this will become 82 minus 2, 80. But if this is 81, that means that also increased by what? By 1. So you say that, okay, the reduction, what will account for that one is the alpha particle. That it was the alpha particle that was emitted. But for that increase in that atomic number, that one increase in that atomic number, that must have been due to the emission of a beta particle. So we have said one alpha and one beta particle has been emitted. But in this case, okay, this is strictly an alpha decay. An alpha particle has been emitted here. Why? The atomic number has reduced there by 2, the atomic mass by 4. Alright, next, in a common emitter configuration, the output voltage is through the output voltage is going to be through the emitter. Okay, it is through the emitter. Alright, final question here. Which of the graph below shows the characteristic of an IV transistor? That is the graph D here. The graph D here shows the output characteristics of an IV transistor. You can see the curve. Okay, you can see how the curve is. So that's it. Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry, and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post UTME or post JAMB exam, and also for crash courses in physics, chemistry, and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at Scholar Fedu. Okay, like and share our content, and visit our website at scholar.com to practice UTM exam and modular quizzes for free. Thank you.